Okay, so this session's on solution methods. And what I'm going to do is I'll talk about what I think is probably the kind of the workhorse method for these problems. Uh-huh. Yes, yeah. Yeah, so the multi-stage is every step is a two-stage problem. Yeah, yeah. Yeah, so I'll mention I'll mention the multi-stage extension, but it's basically just repeating the two-stage problem, but doing it in multiple stages, yeah. So actually it'll be the decomposition methods. Those are the most common, and that's what I'll focus on the most. The other thing is, from just a linear algebra perspective, the matrices for stochastic programs have a special structure, and you can take advantage of that structure. I won't mention the complexity results, but it also gives you better complexity results. So basically, effectively for the linear algebra in general would scale like t cubed or k cubed if k is the number of samples. But there are ways to use the matrix factorization, so it's just linear in k. Linear in the number of samples. Okay, so I'll mention these matrix factorization methods. Some solution methods that are special for these problems called simple recourse problems. This is going to be this is another area where George Danzig made an early contribution, so I'll mention that. And then I'll mention some nonlinear approaches. As I said, I'll do some extensions to multiple stages and to integer problems. Okay. So this is the two-stage model, and this is just to give you perspective on the structure. So the structure is something like this. So think of this as your constraint matrix, the full constraint matrix. So the full constraint matrix has a set, so the A goes up here. So we'd have this, like X would be here, and then these are the Y's, 1, 2, 3. So this would be A. And then we'll have T's that go along. And what is that? Okay, they're practicing. Okay, so T are the linking constraints, and then the W goes along with each of the recourse problems, and it comes in here. But the important thing is everything here is 0. This is where the non-zeros are. All the things in here, the matrix, are zeros. So we call this structure block angulars. This is a block angular structure, that it has blocks that go along the diagonal like that. Okay, so this is rewriting the recourse problem explicitly in terms of the individual. Yeah, there are 3 W's. There's one for each of the Y's. So this would be like Y1, Y2, Y3. For 3 scenarios, yes. Yeah, so this would be like a Okay, yeah. This would be like a 3 scenario problem. Okay, so what the methods do is they try to take advantage of this structure. So the method that I'm going to do first is called the L-shaped method. It's called L-shaped because of this shape up here. It's like there's an L, and that's what it's trying to exploit. It's trying to exploit the fact that there's this long part of the A and the T that link all of the different subproblems. And that forms a structure that looks like an L. Okay, so that's the form of the L-shaped method. And what the L-shaped method does is it basically takes a problem like this and it says, I'm going to replace this recourse function Q by some set of linear constraints. So it's going to linearize the Q and set it up as a linear objective function. So what we do is we rewrite Q as a sequence of piecewise linear functions where we'll take, let's say, we get a first point here. x1 is here. We'll find the value of Q at x1. And then since it's convex, we know that if I put a line at x1 that's tangent to the curve there, it's always going to be below the curve. So that gives me a lower bound on Q. And then I can optimize over that lower bound. So that might push me off in this other direction. Maybe I get the next point over here, x2. Then I go up to the Q function again, and then find another linear support that's just tangent to the curve. It gives me another lower bound. Now I might optimize over that, and maybe I get x3 down here, and then I'll go up, and then get another support, and then optimize over that. So the algorithm successively puts on these linear supports and builds a tighter and tighter approximation of the original function. Now, because every time you're solving this, it's a lower bound because of the convexity. So you're always getting lower bounds. So you always have, it's like a relaxed problem that you're minimizing. So you always have lower bounds at each point in time. This is formally stating what the algorithm is. So the algorithm says, on each iteration, you solve a problem. I'll let theta is taking the place of Q. And now theta has to meet a certain set of conditions. So theta is greater than or equal to some set that's supposed to be L. So it's EL minus a matrix EL times X. Or a vector EL times X. So theta has to meet these conditions. Now there also might be some conditions that it could be that the objective maybe is infeasible. It's infinite outside of some range. So it might be infinite over here. In order to make sure that I always have feasible values, I restrict X to be within the range where Q is finite. So there may be some constraints where I make sure that X gives me a finite value. Those are called feasibility cuts. So these linear constraints on the outside, like this, those are called optimality cuts. And then any constraints that make sure that you stay in a region where you're guaranteed to have a feasible solution in the second period, those are called feasibility cuts. Okay, so we solve this subproblem, and then we'll get a solution. And then the idea is if the solution you get basically tells you that it's you get a solution, And then you go and evaluate Q. If you evaluate Q and you find out, oh, actually it's infinite, you generate, that means that you violated some constraint. So you can generate a constraint that must be satisfied. In other words, you see that one was violated, and now you generate a constraint to satisfy it. If you end up with a recourse function value that's above theta, so that's again like here, if I had ended up here, it would be above, probably the next point would be over here. I end up here, it's above it, so I look, theta would be down here, Q is up here, then I'll add in another constraint. So then we'll add in another constraint on theta, and then solve the problem again, and check. So it's solve, check for optimality and feasibility, adds a new constraint, then solve it, and then check again. Okay, so let's go through an example. Okay, so here's an example. It's basically, it's the absolute value of a random variable xc minus x. So if x is less than or equal to xc, it's xc minus x. If x is greater than xc, it's x minus xc. And let's say xc has 3 possibilities. It could be 1, it could be 2, or it could be 4, each of them with a probability 1/3. So you can think of it as something like this. These are the different scenarios, 1, 2, and 3. So the value that I would get from each scenario is the absolute value of x. This is showing as a function of x. So if c is 1, the absolute value of x minus 1 is this function. And if c is 2, then the absolute value is this function. And if it's 4, then it's this function over here. I average them together because they each have probability 1/3, and I get this piecewise linear function. So this is the function that I want to optimize. So the goal would be to find this point down here at the minimum. But without knowing the entire function, just generating it one of these pieces at a time. Okay, so the function is, again, it's piecewise linear and convex. And notice, if I look at that function, like I said, here's x. Here's q of x. Let's say this is 0, 1, 2, 3, and 4. This is 1, 2, 3. Okay, so the function value, it's, I think it's 7/3 here. And it goes down to 1. All right, and let's see, maybe it's 4/3. All right, so at value at 1, it's at 1. Yeah, and then at 2, I think it's, or maybe it's, let's see, at 1, this one's, it's going to be 1, if x is 1, we get 0 in the first one, we get 1 in the second, and 3 in the third, so that's 4/3, so it's 4/3 at 1. So it's 4/3. Then it goes down and it's 1 at 2. And then at 4, So it's 3 away here and 2 away there, so it goes up to 5/3. Goes up to 5/3. And then it goes off. Okay, so the thing to note is the slope here is 1. The slope here is -1. The slope here is -1/3. The slope here is 1/3. And the slope over here is 1. Okay, you can see that the slope is -1 because it's -1 on each one of those different values there. And then the slope here is -1/3 because it's -1 on the top two, or -1 on the bottom two, and then it's +1 on the top one, so it's -1/3. And then here, there are 2 that are 1 and 1 that's -1, so 1/3. And then over here, they're all 1. Okay, so what we'll do is we'll go through the algorithm. Now the first step, let's say I start off and I don't have anything. I just start with x is between 0 and 10. So the very first point, x, it's a different color. x0 is, let's say, 0. So I start off here at 0, and we'll begin the algorithm from there. Yeah, so I called it x1. Okay, so x1 is 0. So I add in a constraint. So the first thing I'll do is to add in this constraint, which we'll go through like that. So this line is 7/3. The slope is -1. So this is 7/3 minus x. So now we solve the problem that says, okay, I'm going to optimize over theta. So this is like, you can think of this as theta. So theta now is minimizing over this function where x is between 0 and 10. So the next solution you get, x2 over here, is going to be 10. So the next solution is 10. Okay, so now you add in that constraint that applies when x is 10. And that ends up being x minus 7/3. So the next, so I did this was like iteration 1. I put on this constraint. And now I add in the constraint that I get from when x equals 10, and I get this constraint here. All right, and that line is x minus 7/3. And that happened on iteration 2. Okay, so now I have these two. So if I optimize over those two, I get this point down here, which is x3. I guess I'm using superscripts here. x3, which is 7/3. And now the theta is 0. The theta value you get is 0, but the q value is up here, so I know I'm below q. And I'm where the slope is 1/3. So I'm going to add in this line. on the third iteration. And that gives me, this is 1/3, or this is x over a third plus 1/3. So I guess it went through 1/3. Okay, so then I get, that happens on iteration 3. I've got that x over a third plus 1/3. And now the next point I get, this point here, is at 1.5. Or 3/2. So now I've got the point where these two meet. And then I'll add in this constraint. And that's on iteration 4. And that constraint is minus, because the slope is minus 1/3 here, minus x over 3 plus 5/3. All right, and then I get this point. So then at this point, I've got x5 is 2, theta is 1, and q is 1. So I get theta equals q of theta 5 equals q of x5 equals 1, and then the algorithm stops. So the algorithm goes through by putting in each of these constraints one at a time, always minimizing over what is there, and then stopping when your lower bound equals the value of the function. So if you minimized over the lower bound, and that's equal to the value of the function, then you've minimized over the function. Okay, so yeah, so this is the basic procedure for this. Okay, so here's a number of things you can do. So the basic procedure is you sequentially add in these constraints. One thing you might do is to separate the cuts out for each of the possible realizations of the random vector. So that is, I have a separate theta for each of the possible realizations of this random parameter. And then I put them together with the probability of each of those outcomes into the objective with the different theta. And what you can see, if I go back to this example, if I did this for this example, if I had a separate theta for this, a separate theta for that, and a separate theta for the bottom one, on the first iteration, I'm at 0. I'd put in this one, this line, and this line. And then I would optimize over that. I would go out to 10. And then I would put in this line, and this line. And then for each one of these, with just 2 iterations, I will have exactly each of these functions. So then on the third step, instead of taking 5 iterations like this, it only takes 3 iterations, 1 at 0, 1 at 10, and then the last one will be at 2, where it's optimal. So by splitting up, instead of having just one theta on everything together, if you made different thetas for each one of these individually and treated them individually, then you'll identify the function faster. So you'll end up converging faster by doing that. Okay, so this is called the multi-cut method. So the multi-cut method, you split your theta up. So instead of writing it as just one theta, I write it as the probability of each scenario times these individual thetas for each of the different scenarios. Now there's one thing that might slow these down. Like if you look at that first step, we went from 0, which wasn't too far from 2, and then we went all the way over to 10. So we went from 0 all the way over to 10. So we went really far. So if we had a good guess at the very beginning, we would have gone far away from that. So the idea of these regularized methods would be, instead of just having this long line like this, I'm going to penalize being further away from 0 with this alpha x minus my previous x squared. So I'm going to penalize being further away, and that will give me this regularized objective. So this would be like theta is greater than or equal to, what was it, 7/3 minus x plus x squared. So I'll add that on, and so then I minimize over this. I get 2x theta is greater than or equal to that. It's times alpha, times some alpha. So I'd have 2 alpha x minus 1 equals 0. So my next x in this case is going to be 1 over 2 times alpha. Okay, so depending on what alpha is, if alpha was like a 10th, if alpha was a 10th, then I would go to 5. I would, I would go to 5. So if alpha was a 10th, I would go to 5 instead of 10. So I would be closer than I would be if I used just the basic algorithm. There are other things you can do that can make it sometimes go faster. Continuously differentiable. So if it's really quadratic because you have continuous random variables, then Nesterov has a method that which is similar to this method that it adds on a quadratic term. He adds on a quadratic term that guarantees an upper bound and actually can be shown to converge faster. Okay, so these are extensions that can lead to faster convergence. Oh, truss region is basically the same as the regularized method. It's just the dual version of it. It's saying I'm explicitly going to limit. Like if I said my truss region was 5, I would explicitly limit it to not be further away than 5. So as I said, the multi-cut version, you create a cut for each of the samples, and that leads to faster convergence. The other thing that can make these go faster is that you use solutions from one subproblem to help you solve others. So in other words, once you solve one problem, one of go back here. Look at it here. So once I had a solution to one of these problems, I'd like to be able to use that solution in these other problems. Well, you can use the basic information. So the bunching method says, I get the basis from one problem solution, and then I just see whether that basis is optimal for all the other problems. So instead of repeatedly solving it, you just check optimality. You just go and say, here's this basis, is it optimal for all the others? And then you don't have to solve them. You just are checking essentially for, in this case, if all the randomness is in the right-hand side, you're just checking for feasibility. So you just check for feasibility since you know whatever solution you have is going to be dual feasible. You just want to make sure that with the same basis, you also have a primal feasible solution. So if you have both dual and primal feasibility, then it's optimal. So bunching is just going through and checking primal feasibility. That's all you have to do to solve these problems. Another approach you could think of is essentially the dual of this, in that instead of like cutting planes, you start from the outside and you sort of relax the problem. So you always have lower bounds. I could do the opposite, and I could just start on the inside. I could just start here and say, okay, I'm just going to take combinations of this point and this point. And that will always be an upper bound. So you can do upper bounds as easily as you can lower bounds. The upper bounding is called interlinearization. It's because I'm taking points that are on the function and then taking convex combinations of them. So interlinearization is like the dual of the cutting. So this is a cutting plane method. Interlinearization is the dual of the cutting plane method. And now instead of generating new cuts, what you do is you test, is there anything below these 2 points, below the function at these 2 points? So you test for that, and maybe you find at this point here. And now you add that point in. So adding that in is like adding in a new column in a linear program. So this is an approach that's called column generation, that you add in columns, or you add in new points that you could use one at a time. I'll show this in the framework. It's usually done where you think of, instead of x, you sort of transform x. You transform x by t. And when I transform x by t, I call that chi. So you do it in terms of these chi variables, which are the transform of t times x. And then we generate everything in terms of those transforms of x. Since these are just transforms of x. Yeah, I'll mention the simple recourse later. Okay, this is just repeating. So again, we have this just showing that it's in this. If I take the multi-stage model and make it 2 stages, this is how the multi-stage model agrees with the 2-stage model. So effectively, the 2-stage model is 2 stages of the multi-stage. And you can use the 2-stage model in the multi-stage approach, just essentially current stage and next stage, one at a time. Okay, let's talk about the structure of these problems. Okay, so again, this is what if I were to write it out, if I were to write out a 2-stage model as a linear program, I would have this A up here in the constraint matrix. I would have A that multiplies the x, and then W multiplies the y's. So here I have 4 y's. Okay, so this is for each of the different scenarios. And then the T matrix times X relates to the W's, relates to each of these W's. Okay, so as I said, this has a very specific structure because there's zeros all the way over here and zeros down here. So that's a lot of sparsity. So generally, when you're doing numerical optimization, everything is linear algebra, right? You're solving systems of equations. So whenever you solve a system of equation, you want to preserve, or systems of equations, you want to preserve sparsity as much as possible. You don't want to have numbers everywhere, especially if you can solve some of these problems with a million variables. But the only way you can solve something with a million variables is if you have some constant times a million non-zeros. You can't have a million by a million non-zeros. That's just going to be too much. So you need to have something like 10 million non-zeros, but not whatever 10 to the 12th is. What's that? A quadrillion. You don't want a quadrillion. Is that quadrillion? Yeah. Quadrillion, yeah. Yeah, you don't want to have a quadrillion number of non-zeros. So you'd like to be able to preserve sparsity as much as possible. You don't want to add sparsity into these systems. However, if you were just to take this problem, I'm going to call this big matrix, I'll call that A prime down here. So this big matrix of all of these things together, let's say that's A prime. If you were just to take this and not do anything to it and apply an interior point method, like an interior point method is the default in a lot of solvers. So for a lot of solvers, if you just take these problems and attack them directly, then what happens is you take a matrix that has a structure like this, and then you multiply it by its transpose. When you multiply this by its transpose, you get something that has non-zeros everywhere. So if I take So, if I had something like this, A, T, 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 W, W, W. So I've got zeros in all these other spaces. Okay, so I multiply this by its transpose. Okay, so I've got A transpose, T transpose, T transpose, T transpose. I've got zeros everywhere here. Then I've got W transpose 0, 0 W transpose, 0, 0 W transpose. Okay, so I multiply these two together, so I get A transpose up here. I get T A transpose T A transpose. Now over here I get A T transpose, and here I get T T transpose plus W W transpose. And here I'll get T T transpose, and here I get T T transpose. A T transpose, A T transpose, T T transpose, T T transpose, T T transpose plus W W transpose. T T transpose, and then T T transpose again plus W W transpose. Okay, so now you've got something that's totally filled in. So what happens, so when you start off with something that has lots of, so even in 3 stages of these blocks, I've got out of 16 blocks, I have 7 that are filled in. So this is less than 50%. And if I have lots and lots of scenarios, it's a lot less than 50%. It's like 10%. So I start off with something that's 10%, and then when I take it multiplied by its transpose, I end up with something that's 100% filled in. So if I start off with 1 million, maybe it was 1 million by 100, 10%, 100,000. That is going to be a lot worse than what I get down here, or that's going to be a lot better than what I get down here. So I'd like to avoid this. If you just put this into a solver, you get it's slow because now you have to deal with all these non-zeros, and that's going to take a long time to solve any system. But B, when you have so many non-zeros, there's a lot of errors. So just the numerical error when you do the calculation is going to pile up, especially if there are many, many variables. And we can solve systems with 1 million variables. So you wouldn't, probably, this isn't even going to be possible within the machine with 1 million variables. So effectively with this fill-in, these problems, if you just attack them directly, you're not going to be able to solve them. So we have to have some way, we have to look at them in a different way in order to preserve any kind of sparsity. So one of the first approaches was this. It was to say, take each of those, again, I had that X had to apply for all the basic, or all the scenarios. So instead I write X as X for each scenario. So I take X and I turn it into X1, X2 through XK. But now I need to have them be non-anticipative. So I add in a constraint that says X1 minus X2 equals 0. And then X2 minus X3 equals 0. And X3 minus X4 equals 0. So that's what these constraints are. So now when I add in these constraints, when I take this matrix times its transpose, I only get fill in sort of below here. I only get partial fill in. So this reduces the fill in, but makes the matrix a lot bigger. Because now I have to satisfy these constraints at the same time, whereas before I automatically satisfied them because I just had one variable. But this is one way in which you can try to preserve sparsity. So this will try to preserve sparsity, and there are some results like John Mulvey at Princeton had done some work on this. So what we want to do is to try to preserve sparsity as much as possible. The other way you can do it is to try to turn the problem on its head. So basically, instead of doing this transpose times this, do the opposite. Do this transpose times this matrix. So in other words, take the transpose here times the original matrix instead of the other way around. But that's the form that you would get in the dual. So if I was in the dual, I would see the transpose times the original matrix. So what's nice is when I do it the other way, then I don't get the fill-in. I only get fill-in on the top. So I only get a little bit of the fill-in. Most of the sparsity is preserved. So almost all the sparsity is preserved when you do it this way. So often often in these problems, if you want to just solve it directly, it's better to use the dual. Now, some packages actually, I think maybe even MATLAB. So some packages automatically check and they see whether to use the dual or the primal. But in this case, it makes a big difference because the dual has a much better sparsity pattern than the primal problem. And that gives you that can be a lot faster. So it can be much faster to solve these problems using the dual versus using the original primal, since you don't get all the non-zeros that you would have if you hadn't done that. Okay, so we had decomposition methods. Now this is kind of an approach to do good factorizations. What I pointed out here, modified Schur complement, it's just another way to factor this matrix. There are different ways in which to do the linear algebra with these matrices. So I can do the linear algebra using something called modified Schur complement, and that also speeds things up. So that's just another approach that kind of takes advantage, tries to preserve sparsity as much as possible. Okay, so the next method. So this is the simple recourse representation where I've used this notation for the transformation of the x variable. So I take the transformation of the x variable and I call it chi. And so another way to write the two-stage model is to say it's minimizing my current set of decisions plus the expected value of decisions in the second stage with respect to these, we call them tenders. With respect to tenders, which are the transformations of the original variables. Okay, so I've written it here for simple recourse, so that I'm saying that I can split the recourse problem into each individual component of the, let's say the randomness is in the right-hand side. So each individual right-hand side component here. And the value of each of those is like given here. It's the QI value positive times whatever the value of the right-hand side is, minus some function of this tender, and then minus the expectation. Now I'll take the expectation of that. I think this is just the expectation of h. This is like the expected value of h. And then minus its conditional expectation of being less than chi. Okay, so this is the representation if everything just depends on basically the sign of the random value of h minus the ith component of this vector chi. So everything just depends on that sign. And then I can write down explicitly what this is. And basically, everything is fixed. Everything is fixed up here. And this is the only part that varies. Everything is fixed in terms of chi. This is the part that's varies with respect to the expectation, or with respect to the distribution. Okay, so when chi in this case, so chi is this value that comes from the first stage, and it's how we transform the first stage. So this is like the the yield of the crop. So it's like, what is the yield of the crop? That's what, or what is the planting of the crop? What is the planting of the crop? And that's what chi is. Chi is how much am I planting of each of these, or what's the yield of each crop? What's the yield of each crop? How much am I planting, or how much am I yielding of each of these crops? Now, if the uncertainty is on the right-hand side and it's discrete, then this value only changes when I get to when the value of chi crosses the next discrete realization of each age. So I can write chi in terms of the points where it either is below or above each of the realizations. So I've written h, let's say the ith component of h has realizations j from 1 up to however many there are. And chi ij is representing the difference in those realizations. So I can rewrite it with these variables chi ij and then just give them a different coefficient for each one of the chi ij's. And now this is totally a linear program. So now I just take dij chi, put it into the objective. And now that turns this into just a linear program. So I just find the value of these, di's. This is the probability of each of the jth component of variable I. And that gives me a coefficient that goes with each of these chi ij's. All right, now I'll show you this in an example. And as I said, this is an example that was in Danzig's original formulation. So Danzig is the first person to describe these models, these two-stage linear programs with recourse, and he put it in this framework. And the first application he had was for United Airlines, the US airline. And the problem for United Airlines was we have a certain fleet of aircraft. We have so many aircraft that can seat 100 people. So many aircraft can seat 120. And so many can seat 200. And what we want to do is to allocate those aircraft to the different flights. But we don't know what the demand is going to be on all those flights. So we have uncertain demand on the flights. But once we allocate the aircraft, we can't sell any more seats sell any more tickets than the number of seats on the plane. So the question was, how should you allocate the aircraft to the different flights so that you maximize your expected revenue? And it's described in this paper, the allocation of aircraft to routes, 1956. So he solved this problem a long time ago. And he basically used this model that I showed on the previous slide. So the decisions in this model are how many aircraft. So this is the X. This is the decision you make now. How many aircraft of type I are assigned? It's the number of aircraft of type I assigned to route I, or route J. And then you'll have a certain capacity. So this is the number of aircraft, and this is their capacity. So in this case, I'm going to say if my route is Delhi to Chicago, then this is, and I might have more than one flight, so this would be like, how many aircraft what aircraft am I going to put on that route, and then how many passengers can they take? This is the actual number of passengers that I take where I note that, so the y variable, this is the decision afterwards, again, that can't be any bigger than either the demand or the capacity. So it's limited by the maximum or the minimum of the demand and the capacity. And then, as I said, there's these Q's that I calculate, this like the expected price on each route under scenario K. And then, as I said, the demand is uncertain. So under each scenario K, I'm going to have an uncertain demand, and then there's a probability associated with it. So in the second stage, the y variables are either going to be the capacity, or they're going to be whatever the demand is. So I'm either going to have capacity or the demand. And as I said, I can redefine the y's to be the incremental function instead of the chi. I called this w. So incremental functions of w. So the w is the same as chi I had in the previous slide. So I can basically say, well, every time I get, as I increase my capacity, I'm able to take more passengers, and that's going to increase my overall value. So it's going to be something like this. My revenue for the initial capacity that I put on, I'm going to probably get new passengers, or I'm going to be able to accommodate new passengers in all the scenarios. At some point, as I add in more capacity, one of the is no longer, I'm not going to be binding it anymore. So that scenario is going to be limited by its demand and not the capacity, so that drops off. So I don't continue to get revenue from increasing capacity. And then I'll increase capacity until I hit the next scenario. And then at some point, that it's just going to go flat because I'm not going to get any more. I'm at the demand level for each of the scenarios, and then I'm not going to get any more. So I get this piecewise linear objective function in terms of the w's. So this is the way, again, so they were solving this problem in 1956. So, they weren't going to just plug it into a computer program. They had to have an efficient way that they could do it effectively by hand. So they worked really hard to try to simplify it as much as they could. So the way that they thought about it is to say, well, think of it like a network. I have the planes of each type that are coming in. So I've got supply. This would be the number of planes maybe that seat 100, number of planes that seat 120, number of planes that seat 200. I've got a supply of planes coming in. And then as I assign these planes to different routes, there's a gain that's associated with it, which is how many passengers I can take. So as I assign them to a different route, then I'll take the number of planes, multiply by the passengers they can take, and then I'll get the total number of passengers that these routes can handle. Given that I have the total number that they can handle, I can see, well, how much am I going to get how much do I get of this first part, how much do I get of the second part, and how much do I get of the third part. So W1 is the variable that corresponds to this part of the curve, W2 corresponds to this part of the curve, and W3 is up here. So then I get something up here. So this overall looks like, now it's almost exactly a network flow problem. It's a network flow problem, except I have gains on these arcs in here. Now, Danzig had just, at this point, he had a few years earlier come up with an efficient way to solve network flow problems. and the efficient way to solve network flow problems like the transportation method or the transportation simplex method, which it allows you just to solve everything with trees. So you just describe your basis in terms of trees, and then you can solve it, just back solve with simple operations to follow the simplex method. So you said, okay, now I've got almost exactly a network problem. So how can I go about solving it? Well, he said in the network simplex method, what you end up with is that your basis has one fewer arcs in it than you have nodes. So that's why you get a tree. So the basis is always the number of variables in the basis is always the number of nodes minus 1. And it connects all the nodes, so that's a tree. So in the network simplex method, you just use the tree structure. Well, here it's not quite a tree. Because of those t variables, a basic solution actually has an equal number of arcs to nodes. So it has a cycle. And then what he came up with was an efficient way to actually do all the calculations with a cycle inside the tree. And that effectively, there's just a single parameter to solve for. So you solve for this single parameter, and then you can do all the calculations for the simplex method. So there's just one extra equation to solve, and then you can do all the simplex methods. So they were able to solve it. So they were able to solve this problem for United Airlines. It was about 10% greater revenue than what their current allocation had been. So they were able to use this solution in 1956 to come up with better allocation of airplanes for United Airlines. Okay. So this is one approach where you can solve problems actually that effectively could be very large. For continuous random variables, so for most decomposition methods, we assume like finite distributions. But for continuous random variables, we can try something that's stochastic. So I'll mention one thing. I'm going to do more tomorrow on Monte Carlo methods. But I'll mention some methods with where you use decomposition. So what you could do is just to sample. So you could just do sampling of these random, or sampling of the random parameters, and then create approximate, because they're sampled, create approximate cuts, like in that decomposition method. There's an issue, though. When you create approximate cuts, there's some bias introduced. So in fact, so one of the exercises I have for the computation is to look at what this bias is in an example. But the problem is that if each of these is randomly sampled, and you're taking the maximum over them, then you're taking the maximum of something random. Well, if it's randomly large, then the maximum is going to pick that out. So the maximum actually is naturally going to pick out the high error values just based on your sampling. And the more you sample, the more likely it is that you're going to get some randomly very high value here. So you're always going to have bias. So if you just do sampling, it turns out you get a lot of bias. What's bad about this is even if you take a lot of samples, if you have more and more of these cuts, so if your problem requires many of these cuts, then even with lots and lots of samples, the bias is going to take over. So you have to be very careful when you do any sampling in these methods to avoid having issues with the bias. So I'll speak a little bit more about this tomorrow, but I just wanted to mention that sort of the naive thing that you might think of is just to sample from these, but when you sample for these cuts, you introduce bias, and bias can be, can make your problems much harder to solve. So for I'll mention a few nonlinear methods that can be used. So I mentioned trust region and regularized decomposition, and the idea that those limit your search, and effectively you're just adding in this quadratic term that's saying, let's say A was your previous value. You're adding in a quadratic term that makes sure that you don't stray too far away. So you don't get too far away from A. And often that can lead to faster convergence. There's an expense, though, because I started off with something that was just a linear program, and I added in a quadratic. So because I added in the quadratic, that means it's going to take longer to solve. But it could be that I'll save some time. So it's not always good to add in this quadratic term, but sometimes it's good. There are also methods that you can apply this. Actually, you can apply this for any convex program, but you could also apply it when you have piecewise quadratic programs. And piecewise quadratic programs can fit lots and lots of different things. So we could apply this over piecewise quadratic programs and use the same sort of method. So basically that method works for any convex problem. You keep on just putting in these cuts. And you can do it particularly efficiently for quadratic programs. That's I think that's the bottom line from this. I'll mention a couple things that are more general. So a general idea is to use the Lagrangian. But you use the Lagrangian in a different way. So most of the time, what we think about is why do we do a Lagrangian method? We have the base of a problem which is easy to solve, and then there's some complicating constraints. And what we want to do with a Lagrangian is we want to take the complicating constraints and penalize them and put them in the objective. So we're going to do the same thing with stochastic programs. So the complicating constraints are going to be these constraints that are non-anticipativity. So think of those, because those are the ones that say, okay, my decision can't depend on anything that happens in the future. So I'm going to relax that part. And if I relax that part, well, for one thing, if I relax it completely, that means I can just solve explicitly for a given sample path. Solving for a given sample path could be good because it might have a particularly easy form of the problem for optimization. So I'd like to relax these complicating constraints, the non-anticipativity constraints. So the idea is I take the non-anticipativity constraints and I put them into the objective, where here I have W is the, let's say W are the multipliers that go with, that are associated with these non-anticipativity constraints. So I take the X and I put it into the objective, and effectively, when I put it in the objective, I'm going to have those multipliers times x as part of the objective. Now, I'll also put in a term, so this is an augmented Lagrangian method. So I'll also put in a term that penalizes the deviation of x from a feasible solution, or from a prior solution. So one of the methods is you solve this Lagrangian problem where you have a set of multipliers associated with this constraint, and then you have a penalty term where the penalty term is between x and some previous iterate that satisfied all the constraints. And so this version of the problem, you're actually solving a proximal point method. So you're saying this is the proximal point which satisfied all the constraints. So I have a method that satisfied, or I have a point that satisfied all the constraints. Then I solve over a problem that just penalizes difference from that with the Lagrangian in here. And then every time I solve it, I'll update the multipliers, and I'll update this feasible point. The way I do that is I solve this problem and I get a set of x's, and then I can find a feasible point effectively just by taking their conditional expectation. Because what would be a violation of non-anticipativity is that their their value conditional on the current information is different for different future realizations. So I just take their conditional expectation with respect to the current information. So once I do that, then I can get a value here that's feasible, and I plug that into this model. Okay, so that approach of using the proximal point method, that's called progressive hedging, that Terry Rockefeller and Roger Wetz have worked on. Oh, that was published in '85. Yeah, that's a while ago. Yeah, so this algorithm, this progressive hedging algorithm, is an interesting algorithm because it iteratively updates your x and your dual variables, or multipliers w, or and then this proximal point. So you have this point that is feasible, a set of multipliers, and your best guess of the x's. One of the big advantages is that if there was some problem structure in the deterministic problem, you maintain all of that. So if the deterministic problem was relatively easy, like a network problem, then it's still going to be a network problem when you solve it here. So that creates an efficiency too. So these progressive hedging algorithms, they've been used in a lot of different problems. One that a lot of people use them for are electric power problems, which I'll talk about in the last session. But in those electric power problems, you have lots and lots of generators, and you're trying to decide when do you turn the generators on, when do you turn the generators off, and many, many time periods. So it could be a whole week, so like 168 hours worth of time periods. And so you'd have 168 different stages of those problems. And they solve it with this by decomposing each one into individual plants and individual scenarios. So all I have to do is to decide, and effectively it's like I have a price for the electricity, and each plant decides, depending on what the price is, should they turn on or turn off. And so for each plant, one at a time, it's very easy to solve. You solve it immediately. Because it's so easy to solve this, that's why these algorithms are so popular. And those it just decomposes into just solving one plant at a time. I will say, though, there's those problems also usually involve integer variables. And if there are integer variables in these, and then you round them, it's not guaranteed to converge. So even though people use it a lot, even when these variables are supposed to be integers, it's not guaranteed to converge, and so most of the methods have some heuristic to ensure that they actually converge. There are other ways to get around that, which are like using other kinds of Lagrangian, and effectively you have to do something for the integer variables, like branching, which is another way to solve those problems. Okay, now I need to mention, I wanted to mention a little bit about multiple stages, particularly because nested decomposition was the topic of my dissertation, so so I have to mention it. But basically what nested decomposition does is it just repeats that two-stage decomposition method for every stage of a multiple stage problem. So at every stage of that multiple stage problem, you have the same sort of setup where you have this variable theta that represents what happens in the future. You have your current set of constraints, and then you have these cuts, these inequalities that are placed on theta, or approximating the recourse or value function at each point in time. And so you're sequentially updating and adding in these cuts. These are the ones that maintain feasibility. These are the ones that are associated with optimality. You sequentially add them into your problem and then resolve. And what you do in these multiple stage problems is you can do a lot of different moves in terms of either you go forward in time or backward in time. But if you go forward in time, then you take your x's and you pass them down to the next time period, and then the next time period solves, and then at that second time period, it creates new constraints and sends those constraints back. So then when you go backwards, you take those constraints and resolve these problems. You may send a new constraint back to the previous time period, or you may send your decision variables, down to the following time period to get new constraints. So they iterate back and forth across time, and sequentially are solving, but they're sequentially solving a bunch of these two-stage models. So they're always doing something one stage at a time. I'll just mention that these also can be used to solve infinite horizon problems. So in an infinite horizon problem, basically you're looking for a solution, like in a Markov decision problem. You're looking for a solution that's valid for any given state. So if I'm trying to control a plant, and I don't know what state my plant's going to be in, I just want to have a decision for any, let's say, any power value, how much am I going to produce from the plant? So I just need a decision for each of the possible realizations that might happen, and I want to do that for any possible state that I might be in. You can do the same sort of thing. I make approximations of the value function at each point in time. I start off with a bound on the value function. I make an approximation of it. I update my approximation. That's what this TVK is doing. And I'm trying to get to the true value function. So I'm always taking my previous approximation, I'm making an update on it, adding in a cut, which gives me a new approximation, and then, again, evaluate that, add in an update. So T is like my step to evaluate it. Every time I evaluate it, I add in a new cut. as long as, this is the discount factor, so as long as the discount factor is sufficiently large, it turns out that these, well, as long as the discount factor is sufficiently large, it turns out that this algorithm also will converge and give you the unique fixed point, which is the value you're in search of. I will say sometimes, so this is showing convergence, so it's making cuts, making cuts, making cuts, making cuts, and then giving you, this is the value function. So it's approximating the entire value function, so for every given point, you're getting all of the, exactly what the value should be at each of the possible states. So it's solving for all possible states. So it's really trying to fill, not just find the, let's say, the minimum one here, but to fill in everything. So it's sequentially getting all of these cuts and then filling in everything. Although sometimes it takes a while. So sometimes you're adding cuts, adding cuts, adding cuts. This is like 100. And I'm only getting, I'm still not exactly fitting the value function here. Here, I guess that's up to whatever it is, 500. So sometimes it takes a lot of cuts, but the method does converge. Okay, and then the last extension I wanted to talk about is just with integer programs. So if everything is just in the integer variables, then you can use the same, or everything is just in the first stage. Then you can use, everything sort of remains valid. So you can just use the basic L-shaped method. You might have some branches for your first stage variables, but that basic method that I gave at the beginning, that basic decomposition method applies here the same way you would apply it without integer variables. But the only thing is you'd have branches associated with the integer variables. The cuts themselves, though, are always valid. So whenever the cut only refers to the value of x. So the cuts remain valid. So you can use the cuts in all the branches of the tree. So whenever you get a cut in one branch of the tree, I can apply it everywhere else in the tree. So there is some efficiency by using this method, since those cuts are valid everywhere. If the integer variables are in the second stage, then it becomes a little bit more difficult. You may have to branch on, you can branch on possible values of your x, and that may affect what happens in the second stage. The other thing you may want to do is to add in inequalities in the second stage to prevent having fractional solution. And what you'd like to do is to add in inequalities that are going to guarantee that you don't cut off, well, you cut off fractional solutions, but you don't cut off any integer solutions. So you want to add in inequalities that don't cut off any of the integer solutions. Okay, I'm going to mention this. This is just saying how you go through the L-shaped method with integer variables, but it's basically it's just the same as the standard L-shaped method. But let me mention about the valid inequalities. So what we might have is, let's suppose our variables in the second stage can be either 0 or 1. So when you do a branch on those variables, the simplest way to do the branch would just say either y is going to be less than or equal to 0, or y is greater than or equal to 1. So in other words, I'm going to cut out all the fractions in y. Now I know for sure that my whatever optimal solution I get has to be in the convex hull of the values that are feasible where y is less than or equal to 0, and the values that are feasible where y is greater than or equal to 1. So I know it's in the convex hull of these two things. So now if I ever come up with a solution, suppose I've added in some inequalities and I've solved my problem, and I come up with a solution that's not in the convex hull of the union of these two polytopes, this polytope here and this polytope down here. So it's not in the union of those two things, or even in the convex hull of the union of these two things. What I would like to do is to find a constraint that cuts off this value y nu, and that will be a valid inequality. An inequality that ensures that I don't end up at this point again. I've got a fractional solution. I know it's separate from any of the feasible solutions. I want to cut it off and not cut off any of these feasible solutions. So in other words, I want a constraint with pi and pi 0 such that if I'm in the convex hull, where my true value might lie, that value satisfies the constraint, and the value that I want to cut off doesn't satisfy the constraint. So I want to have this kind of constraint. Well, what you can do in stochastic programs is to take advantage of the fact that they have similar structure and use one test to get a valid inequality for all of the scenarios. We want to do one test and then get something that works on every single scenario in the problem. And that's the idea of a common cut coefficient. So I find a common pi that separates, if I have that separates all theykj's that are fractional. I want to have a common pi that separates all of them by solving just a single problem. So this is just a formulation that solves a single problem that generates a valid inequality. So I can solve one extra linear program on each step and generate a valid inequality, and that reduces the set of possible solutions I have to search through. Okay, so let's wrap this up. Okay, so all of these solution methods, everything that I talked about, even with integer programs, what I'm doing is using convexity. So they're all using convexity in some way. So all these methods are based on exploiting convexity. So when we have convexity, we want to use it as much as possible. All these methods are trying to use convexity in different ways. Building these approximations is the fact that because I can put these linear constraints on, and I know they're always valid, that's all due to convexity. And convexity gives us global information, and you can apply them in models with integers. And in those integer models, there may be ways in which, because of the structure of the problem again, you can take advantage of integer techniques, such as valid inequalities, and make them even more efficient. So, so these are all different things that you can do with convexity and stochastic programs. Okay, any questions? Okay, so I'll have some exercises where you can use MATLAB. I have a MATLAB program that does the L-shaped method. And what you can do in those exercises is look at what happens if you try sampling cuts versus using the L-shaped method itself. What you'll see is, it takes a lot of samples to get something accurate. So that I think that'll be a good kind of exercise to go through. And then, tomorrow I'll talk about Monte Carlo methods. So I have some exercise with the Monte Carlo methods as well, particularly because those are the things that are used in machine learning. So what I'll talk about tomorrow are those methods that are the most common things people use for like neural nets, deep learning, machine learning. Those are the methods that I'll talk about tomorrow. Okay, thanks.